we are going to discuss about the speed control of DC motor. As you know that the back EMF of the DC motor is nothing but EB equal to Vt minus IaRa. Okay, so again from the speed equation we can know that the back EMF EB equals to Ka phi omega m. Here omega m is the angular speed, phi is the field flux. Okay, now equating both these two equations, we can write that the omega is Vt minus IaRa by Ka phi. Okay, from actually we written this equation, that is the speed equation of the DC motor. So basically from this equation we can conclude that the speed of the DC motor can be controlled by the variation of armature circuit resistance, by the variation of the field flux. Okay, that is inversely proportional. If field flux is increased, speed is decreased. Okay, again the terminal voltage, that is linearly proportional. Okay. Before we started the speed control of DC motor, we have to know 5 basic important terms that is very important in case of speed control of DC motor. So the 5 terms are base speed, speed regulation, speed range, constant power drive, constant torque drive. So what is base speed? Base speed is the speed, that is actually it is the nameplate speed. Okay, it is the speed at rated armature terminal voltage and rated field current. Okay, now the speed regulation. Speed regulation means if the motor speed change no load to full load, suppose del of omega n. Okay, changing the speed from no load to full load, del omega n. So that change speed to the base speed, this ratio is the speed regulation, that is del omega m by base speed is the speed regulation. Okay, now speed range, it is nothing but the ratio of maximum allowable speed to the minimum allowable speed. Next one is the constant power drive. If the shaft power is constant for a given speed, then the system called the constant power drive. Again, if the shaft torque is constant for a given speed, then the system is called constant torque drive. Now the speed control of DC shunt motor by armature resistance control. First of all, the schematic diagram of a shunt motor. This one is the schematic diagram of shunt motor. That is the shunt field. We are applying the terminal voltage Vt here. This one is the armature current and this is the field current. Okay, now when we are not inserting this resistance in the circuit, that is the external resistance in the circuit, that time the armature current, that is first armature current, suppose Ia1 is nothing but Vt minus Ka phi omega 1 by R. Here omega m1 is the first speed. When inserting the Rg resistance, external resistance in the armature circuit, we are taking that at beginning the speed is not changed, that is taking first speed omega 1, at beginning the speed unchanged, that is omega m1, but the current is changed due to inserting the resistance Rg. So Ia1 dash is Vt minus Ka phi omega 1 by Ra plus Rg. From these two equations, we simply conclude that the Ia1 is smaller than Ia1. Okay, sorry, Ia1 dash is smaller than Ia1. Now if we are increasing the resistance, increment of resistance value, that is the decrease of armature current. Decrease of armature current means torque of machine, electromagnetic torque of machine is reduced, so that the speed also reduced. So we are increasing the resistance here, that is Rg3 is the higher resistance than the Rg2. Rg2 is the higher resistance than Rg1, so that speed is linearly decreased. Okay, increment of resistance, external resistance, that means speed is linearly dropped down. Okay, now for constant load torque, if your shaft load is constant, okay, shaft load is constant. In case of shunt motor, we are already known that the field flux is constant as the field connected parallel with the circuit. Therefore, for armature current is changed from Ia to Ia1. That means the electromagnetic torque is reduced from K phi A1. This is the first time torque and this is the second time torque. Okay, K is the motor constant, is the constant. Phi is the shunt motor flux is constant. We are changing the current Ia1 to Ia1 dash. Here Ia1 dash is less than the Ia1, so that the electromagnetic torque in second case is smaller than the first case. Okay, so electromagnetic torque reduce means that the speed at now is decreased. Speed decrease means we are know that the motor back EMF equation K phi of omega m. As the omega m is reduced, back EMF is reduced. As back EMF reduce, any motor equation that is Ia equals to Vt minus Eb by Ra. So Eb reduce, that means the increment of armature current. Carefully noted down, Eb reduce at now, so that the armature current is increased at now, increase up to its initial value for the constant load torque condition. Okay, now if we are taking both the speed, that is for second time speed, taking omega 2 and first time speed omega m1, in both cases that time the speed is changed, the ratio of both these two speed is omega m2 by omega m1 is Vt minus Ia1 Ra plus Rg and divided by Vt minus Ia Ra. So from this, if we are equating this equation, from this we can generally conclude that the second speed is less than the first speed. Thus, for the speed control and constant load torque, we can conclude that the armature current drawn from the supply for a constant, also power delivered from the supply means to the motor does not change and remain constant whether external resistance is in circuit or not. Power delivered to the load, that is second case, P2 equals to suppose Ea2 into Ia1, so power delivered in second case is decrease is proportional to the speed decrease. Now speed control of DC series motor. So here we draw a series motor, series field is connected. Okay. Now before introducing the RG, that is the external resistance, the terminal voltage is Vt equals to K phi omega m, that is the first field, plus Ia Ra plus Rs. This is the series field. If we are taking the saturation is neglected, as field is connected in series with the circuit, increment of armature current, that means the increment of field current. Here field current, armature current are same, so flux is increased, vice versa. So phi is linearly proportional to the Ia. Taking saturation is neglected, so phi equal to C of Ia. C is the constant, so that the equation is Vt equals to Ka C omega m plus Ra plus Rs into Ia. Now this one is the first field. If we are equating the first field, Vt minus IaRa, that is the first time back EMF, divided by Ka phi. Actually phi is Ia. Okay, phi equals to K of Ia. K is another constant here. Okay, after inserting this value, terminal voltage, just we are adding the RG resistance here and the another current value IA2, the second current value A2. Okay, if we are taking the constant load torque, that means the torque K phi 1, that is the first time torque, equal to K phi 2 A2, that is the second time torque. Okay, this is the phi 1 is the linearly proportional to the Ia1, and phi 2 is the linearly proportional to Ia2, that means KCIa1 square equal to KCIa2 square. Okay, so Ia1 equal to Ia2 for constant load torque. These two current are same. Now again omega 2 should be Vt minus Ia1. Here we writing why we are writing Ia1, and that is the Ia1 equals to Ia2 here. Okay, so Ra plus Rg, just inserting Rg, and this one is the K phi Ia1. Now ratio of these two, that is m2 by n1 or m omega m2 by omega m1, that is this equation. Okay, so from this equation we generally conclude that the omega 2 is less than the omega m1. Okay, from this equation we generally conclude that the omega m2 is less than the omega m1. So from here we see that just inserting the external resistance in series with the armature circuit, the speed can be controlled in case of DC shunt motor and in case of DC series motor. So that more speed regulation is not much important in case of series motor. This type of control are very cheap and can used in crane, traction purpose, that is train, etc. So this is the speed control of DC series and shunt motor by variation of armature circuit resistance. Thank you. If you have any query, please contact with me. Thank you.